Today we're going to look at this example that you see on the screen, and on the left hand side you have an electrical system, you can see here, and on the right hand side you have this mechanical system. You have a set of equations that you see on the left hand side, and you also have a set of equations that you see on the right hand side. You have a differential equation on the left hand side that belongs to the system, and you have a differential equation that you see on the right hand side that belongs to this system. What we are going to do today is to explore how those equations came about and what are we going to do with those equations, both for the electrical system and the mechanical system. So let's take one at a time and we'll work it out. What I want to concentrate on this is how this thing came about. So what I'll do is I am going to take this picture in here. I will go to my OneNote in here and create a new page with this example, and we'll go from there. All right, here we go. Very good. So let's put a title here. Let's call it Understanding the Differential Equations on an Electrical System. So let's just you can make some annotations that allow us to understand the system a little better. This is a C element, this is the inductor here, and we have the resistive element in here. What's happening here? Maybe we need to move it a little. It's not allowing me to write on where I need to. So let's try again. Let's try again, and this time I will do it with a little more colorful. So this is C. This is the R element. This one is the but the R element is on this side. And then this other one in here is the inductor, but right now I need to erase it. Yeah, there we go. So we're gonna, this is L right there. And this is your voltage source V. Okay. So what we need to do is to apply, you may say, first of all, to be able to use this method, we need to, let's just put a set of steps in here. I like steps. I think it's always a good idea to to have steps in here. So let's put the title steps. I like on the right hand side over here. So the first step is going to be to apply for a circuit. One, you're going to say apply on each loop Kirchhoff's laws. Kirchhoff's laws, yeah. So we'll apply the Kirchhoff's laws in there, and but that's gonna be for each loop. Mm. So how do we do it in this case? Let's just start over here. In this case, we're going to say that the voltage is equal to the summation of the voltages on the voltage of the resistor plus the voltage of the capacitor plus the voltage of the inductor. So this is the application of Kirchhoff's laws. In this case, is saying perhaps to be a good idea to write down the summation of all voltages around a loop should be 0. That's the idea, huh? All right. Which is the same thing as saying the source equals to the summation of all the other voltage drops. So we have some basic equations, basic laws to be able to know what each one of these are. Yeah. Like for example, in this case, the voltage of the resistor is the current I times R. Yeah. Is the current that you see around the loop in there. See the voltage around this loop is that I'm talking about. Then you have the voltage of the capacitor. It's like 1 over C times the integral of I dt, right? Yeah. And the voltage of the inductor is I times, no, L times di dt, right? So these are the very basic concepts upon which each one of those elements, maybe we will put it here, elements basic equations. In other words, this is how each one of those is defined. That's what it does. All right. So if we keep on our steps, we say, then we can say this is number 2. So it's going to say that this is right. This is called constitutive laws of each constitutive laws of each element. And we can say and the relation to the voltages. Very good. So if this is true, I am going to say, okay, let's just draw a line in here, and we'll just write it in here. We're going to say voltage then is equal to I times R plus 1 over C times the integral of I dt plus L times di dt. You see, if you look at this equation, there might be difficulties in using this in this format. Why is that? The reason is that this equation mixes integration and differentiation. And in this form, it's not as easy to manage this. The best thing to do is to have a differential equation only, not one that has mixed integration and differentiation. Okay, so how could we cure that? The way we do that is by writing, not changing it, just writing the same equation, but in terms of the charge. So if we have something like this, where we have that I is dq dt, then it's gonna work, because you see we will write that voltage is equal to dq dt times R plus, this would be 1 over C times Q, right? The integral of I is Q. And then plus L times D, this would be D of dq dt, d dt, dq dt, like that. Now it's looking a little better, because now I can write that V is R times dq dt plus 1 over C times Q plus L times d squared Q dt squared. And now you see you have strictly a differential equation. See? So this one in here is the second order differential equation of the circuit. So this is called is called second order differential equation. Okay, very good. Now we compare it to where we were in the previous slide that I had where I was explaining this. You see, now the equation makes sense, right? Because this equation that you see in here is basically what we derived. And so now we can actually use this differential equation and transform it into a Simulink block diagram and go with that. But you see, I think it's not a bad idea that just as we looked at the one on the left, we look at the one on the right, although in a prior video we already saw that. It might not be a bad idea to, for the sake of comparison, to develop the other equation. But this equation here is the equation that I have on the notes in here. Huh? Okay, thanks. If we look at the other one, in here, maybe what we should do just to be consistent, bring the picture here, the same one that we're doing. And in fact, that's what we should do. We go and bring this one over here to this note in here, and we'll do the same thing. I would say let's just put the last step so that we finish this in here would be to write the differential equations in terms of the charge. That's what we have now. Okay, on this other case, what we're doing is we're going to create the free body diagram over here. We have the mass in here, we have the force in here, and we have the other one in here that says k times x, and this one is v times x dot, like this. So in here we also do the same thing. The summation of the forces in this case equals to summation of the forces equals to the rate of change of momentum, like this. So if you write now, if you write that, you say F is equal to, no, F minus k times x and minus b times x dot equals to mx double dot. this is the same format that we have over here, because you see we have the way we have this over here is this the input and these are the outputs basically. But this is the way we derive the other equation using the same method. And this would be the representation of that. So what I envision is for us to be able to do a simulation of either one of these. See, there's the way the equations have been organized are from the highest derivative to the lowest. Perhaps it's not a bad idea to do it in here so that you can actually be able to observe it on the same way. What I'm saying is the equation is written a little differently, like it's L times d squared q dt squared plus r times dq dt plus 1 over c times q equals to b. This is the way it's written. See, this other one has also been manipulated mx double dot b times x dot like this, see? And therefore it has this form or has this form. And both of those were the ones that we saw on the slide, see? There you go, see? For both systems. What I am going to do right now is to use the equations for the electrical system and put them into Simulink. Let's see how we do that. Well, so we're going to be working with this one, without the equation. So just so that we don't confuse things, I'm going to draw a line in here, and we say use the equations of the electrical system. And then you go to Simulink. Okay. So a block diagram is always a representation of a mathematical equation. I think that I am going to write it down in here, possibly with this thing, so that you'll remember. And let me just see, block diagram is a representation block diagram is a representation of the mathematical equations. Very good. So we need to insert this. So a block diagram is a representation of the mathematical equations. If this is true, then what we need to do is to go over here and create a summation here, just like we have it on up here, right there. And you, in this case, you will say it's better to have the all this derivative, you know, like this one, like L Q square dq is no d square q dt square. I'm going to interfere with my drawing, so I think I better erase this. But rather we'll go and say, okay, I'm looking at the electrical equation, okay? This is the this is the input here. The output, this is LD square Q dt square, and this will have to be, each of this will have to be a minus, like minus R times dq dt, and then you have this other one here is minus R times dq dt. Okay, so once you have this, it's easy to see that you could multiply this by L, and this would be d square q dt square, and you integrate it once, and then you have dq dt. And then this dq dt. We need a scoping here. See this, not only we need the scope, we need another integrators. I need to put it in between, so I am gonna erase this guy, and instead I am gonna write down another integration which will bring us the solution to just q. So if you do that, okay, and then on the other one, you see here, I have a little problem here, I went too fast. This one needs the variable r in here, and this other one, yeah. So on this one, the answer to this is going to be, I mean, the value here is b. And so this is what we would transfer to Simulink. right here. So using this, we transfer it to Simulink, and then we can do the simulation, see? So that's how we generate the block diagram, and we generate the, the equation of motion. So to complete this, I will have to do it in Simulink, and I think I'm gonna make it such way that it's a little smaller so I can see it while I work out in Simulink. We're gonna close this and we say, okay, look, we need the MATLAB. Turns out that yeah. So if you do Simulink in here at the prompt, you're going to get this. So you click over here to create a new model, and then what I would do is I bring in all the ingredients that I need. Need like 3 of those, 1 of these. We need a summation point. Okay. Okay. So we have those. We have the 2 integrators that we need. We need this too. How many variables around the loop? 4 of them, right? 1 positive, 2 negatives. So what we do is on the summation point, we go and we say, yeah, 1 positive and 2 negatives. Yeah. So we'll connect this one here, and this is going to be the big voltage V. Yeah, V. Very good. So let, there you go. There you go. This, if you do a control I, and it will flip, and if you do a control D, it duplicates. Or you could do copy and paste too. There we go. So in here, you have just what was 1 over C. One over C. and then this other one will be connected here and then connected over here, and this one connected here, and then this one connected over here. So all we have to do to get the simulation going now is to put some numbers. And the way you do that, this one, what was the number here, is R, right? And if you put the numbers on on the window, like R, for example, equal to 1, then you have like C is equal to 30, then you have R and C. This is the problem. This is not C. This is L. So V is equal to 10. And what else do I need? An L, right? No, L is in capital. Remember, it's case sensitive. If everything went well, being in Simulink over here, I should be able to run this. You know, this is the scoping here, and if I click on run, probably we didn't give us any crazy answer, but did what we needed to do for the values. Okay, so that's how you do it, from scratch all the way to the simulation in Simulink.